Our next talk comes from the same research group, and it's on TAPER, a contextual tensor-based approach for personalized expert recommendation.
Good afternoon, everyone. I'm Hancheng, and a PhD student from the Texas A&M University. And last talk, my lab mate Haokai has talked about how to find the text for users which can describe their expertise. But in this talk, we focus on recommending the personal experts to users. So these two problems are very, related, but fundamentally different. So there is a long history for item-based recommender systems for specific items like movies, songs, news, and so on. And recently, we have seen a lot of the interest on high-quality content producers, so who just curated very great content on social media platforms. Given this large space of users, can we identify some of those who are high-quality content producers? So our goal in this work is to recommend these experts to the right person. So this problem we called personalized expert recommendation. So let's take an example. For example, there are 3 users. Select Hillary and Trump and President Obama as his experts on the politics. And the 3 other users select Zuckerberg and Elon Musk and me as the experts on the technology. So given this information, so we can treat the user expert topic preferences as a tensor, which is the multi-way array. So traditional matrix factorizations cannot simultaneously consider all dimensions. So we just apply the tensor-based approach to crack this personalized expert recommendation problem. So given the observed tensor, the tensor x, the t, so based on the factorization, we can estimate the completed tensor data. So all recommendations will be given from this estimated tensor x. So, however, we still face so many challenges. So first of all, we focus on the personal experts rather than the general topic experts with broad appeals like the top 10 doctors in Boston. So we focus on the personal experts. So secondly, since few users provide the feedback in terms of the quality of experts, so the data is extremely sparse. So thirdly, there are complex relationships between users and experts and topics. So how to address these challenges in this problem? So our idea is to leverage the rich contextual information. So there is many possibilities in context. But in this study, we only focus on the 3 important contextual factors, which are social connections, location, and topics. So we naturally ask, how do we model these contextual factors? And how do we integrate this modeled contextual preferences into the tensor-based model? And which factors are most important? So before I dive in details about this context, so I will briefly introduce about the Twitter list. So Twitter list, we use the Twitter list, geotag the Twitter list as the data in our study. So Twitter list is a curated group of Twitter accounts created by users themselves. And for example, the Alan put Elon Musk and me in his list technology, and Jane put Jamie and me in her list foodie. So given this information, we know these users may be interested in like technology or food, and also we know which people can be recognized as their personal experts. And by aggregate this information, so I was labeled with technology and food. So we will treat, which can be treated as my expertise. So okay, back to the context. So for example, we know there is 3 users, Jane, David, and Ryan, and we know their preferences of personal experts. So since the Jane and the David are geophysically closer, so we can see they have the more similar preferences on selecting the experts rather than the Ryan. So from our Twitter list data, we can see that the different locations, users in different locations have different levels of locality on selecting experts. So we can see the geospatial context does affect the user's preferences on experts. So for the topic context, we still have the Jane, David, and Ryan, but we know the Jane and David has exactly the same topic of interest. So as we can see, Jane and David have behaved more similar on the selecting experts. So from our Twitter list data, we observed the more the topic the 2 users shared, the more similarly they behave on the selecting the experts. So we can see that the topic context does affect as well. So in terms of the social context, so we know, if we know Jane and David have a stronger social tie, so we found they have a more similar personal experts rather than Ryan. So from our data, we observed that the users who follow each other has a more similar preferences on experts. So the social context does affect the preferences for experts. So next, we will ask how to model these contextual factors. So we have the users, experts, and topics. So there is 2 kinds of a relationship we should notice. One is relationships between, we call homogeneous entities, like between the users and the users, experts and experts. So given the contextual information, we model this information between the homogeneous entities as a similarity matrix. But the other relationships is ones between the heterogeneous entities, like between the users and the experts, users and the topics. So which can be modeled as with the adjacency matrix A, B, C, for example. So once we, due to the limited time, I'm sorry I can't just provide like more details about this modeling. So if you are interested in details, yeah, we can discuss offline. So once we have this modeled contextual factors, contextual preferences, how can we integrate this? How can we integrate them into our tensor-based framework? So once we have the basic tensor-based recommendation model, so first of all, we added the relationship between the homogeneous entities by trace-based regularization terms. So in terms of contextual information between heterogeneous entities, we add them as a regular penalty terms into our objective function. And this is our model called TAPER. So we build an efficient algorithm based on the ADMM, which is standing for the alternating direction method of multiplier, to solve this problem. And all recommendations would be made based on the estimated, the complete tensor X. So in the experiment, we compared for the baseline method as well as for variations of our the tensor model TAPER. So the G-TAPER means that we only considering the geospatial contextual information, and the T-TAPER means we only consider the topic contextual information, and the S-TAPER means we only consider the social contextual information. And our model TAPER consider all three kinds of contextual information. So first of all, we can see, based on the result, we found that without any contextual information, tensor factorization has a better performance than a traditional matrix factorization. And then we can see the TAPER has a clear win comparing with other baseline method. And next, we just comparing the variations of our proposed model TAPER, and we found that the social ties of users and experts provide more significant contribution to the personalized expert recommendation. So, and furthermore, we also evaluate the impact of the contextual preferences, which means the relationship between the homogeneous entities and the relationship between the heterogeneous entities. So we found the contextual preferences between the homogeneous entities plays a more important role than ones between the heterogeneous entities. So last, we also check the consistency of our proposed model, TAPER, and by varying the amount of the training data, we found our proposed model TAPER consistently outperform both matrix factorization method and the pure tensor factorization method. So let me conclude this work. So in this work, we found the user of the contextual information can lead to improve the accuracy of personalized expert recommendation based on a tensor-based approach. We also found the social ties of users and experts provide the more significant contribution. And last, we found contextual preferences between the homogeneous entities play a more important role than ones between the heterogeneous entities. And in terms of the future work, so we are trying to integrate additional contextual factors, such as temporal factors, into our model. And the other one is I think also is very important, is developed a distributed, parallelized version of our proposed model TAPER. So this work is underlying right now, so hopefully it can be finished next month. Yeah, I think that's it, and thanks for your attention.
Questions?
Thank you for the talk. What do you think that it can recommend genuine experts as opposed to reinforcing popularity bias?
Can you say again?
Would you say it can find real experts as opposed to just finding who is popular and just making them more popular?
Actually, it's not very limitation or just a restrict limitation for, hey, you cannot recommend the general popular expert to users, but we put more focus on because sometimes it's a long tail, right? We put a lot of focus on the tail part. So it doesn't mean we cannot recommend popular users. Because sometimes, for me, I will just follow the famous people like Zuckerberg, Elon Musk, right? So they can be considered as my personal experts as well. But maybe the Haokai, I put Haokai in the technical list, so Haokai may be another my personal expert, so based on my own preferences. So it's not very just an obvious limitation to discount with.
Maybe I'll just piggyback on the last question and
Sure.
ask something sort of similar.
Sure.
Is that, so obviously, since you're looking at personal experts, it's possible that, say, somebody can be labeled as a technology expert for users ABC, and somebody else can be labeled as technology experts for users XYZ.
Yeah.
Does the context information, can it be used to sort of reconcile and maybe rank them globally, in the sense that now we have two experts, they're experts to different people, but is one better than the other, and can that sort of contextual information can help us disentangle that?
Yeah, yeah. It's a good point, actually. So sometimes we're trying to combine some global experts and some local experts together, right? Sometimes it's just as I said, it's a long tail. You cannot only focus one part of them. You can only focus on the rare experts, or you cannot only focus on popular experts, popular users on social media platforms. So we're trying to combine them together. So that could be a good way to solve this problem. Yeah.
Any last questions?
Hi, thanks for your presentation, Hancheng.
Thank you.
It was great. So I wasn't able to break down the regularization component that you put up. But is there a piece that specifically addresses kind of a loopy propagation? Since you're since you've got kind of a loop structure, there may be a potential for maybe popular things to reinforce themselves.
So I will go to this part.
Right.
Yep. So actually, I'm not sure it can be just associated with the reinforcement learning you mentioned, but so far I just want to provide is a general framework to combining or to integrating the contextual information. Yeah, usually we have contextual information between the homogeneous entities. And meanwhile, we also have the contextual information from the between heterogeneous entities. I think these two kinds of contextual information are pretty general. So no matter what kind of application you want to try to address or try to correct, so you can try to put this contextual information into this general framework, try to correct it, try to solve it. That's my hunch here. So I try to make it very general and not specifically focus on like a specific application.
I see. Thanks.
Yeah. Thanks.
We have time for one last question.
Go ahead.
Hi, nice talk. I have checked the paper, and you don't mention the state-of-the-art competitor in terms of the tensor factorization. Mm-hmm. So can you give us more details?
Oh, sure. Actually, I have a paper we published in the CCAM in this October. In that paper, we compare different like state-of-the-arts about like tensor method. Yeah, so it's a similar framework. So why I didn't put some like state-of-the-art of tensor method here is because we want to focus on like a traditional recommendation method, matrix factorization, and what's a tensor-based method. So in this study, we compared like without any contextual information. We use the pure matrix factorization method and the pure tensor factorization method. So we found the tensor-based factorization method has a much better performance than the traditional matrix factorization, at least for our application, by using our data right now. And so our focus is on comparing the tensor-based approach with other like traditional ways, not focus on like a comparison between the tensor-based state-of-the-art tensor-based method. So that's my intention here. Yeah. Thank you.
Thank you.